Alright, for this next video, we are going to combine examples 2 and 3 because how you approach them is basically identical. So let's get started with example 2, and then we'll just copy and paste our logic over into example 3. So unlike example 1, in this example, we are not given an inequality to start with. So we are going to have to come up with that inequality on our own, and that can be a daunting task at first. But it's a skill you're going to have. You certainly use it a ton in this class, and also, again, you use it a lot in Calc 2. So here's what I think when I look at this. I see that there is a sine function. Let's for a minute forget about what is the argument of sine. So forget that we're taking the sine of 1 over x. Let's just put blinders onto that for a moment and just take a look here at this fact that no matter what you take the sine of, so I can just say sine of anything is always going to be a number between -1 and 1. No matter what you put in there, that's always true. So if this is true for anything, in particular, it has to be true for 1 over x. So that right there is what gives us an inequality to start with. But now the thing is, we can't use the squeeze theorem quite yet because we want x squared times the sine of 1 over x. We don't have an x squared in here. Well, why don't we just put one in there? This is a compound inequality. We are allowed to multiply it by whatever we want, as long as we multiply each portion, left, middle, right, portions by that same term. So if we multiply by x squared, so this inequality here implies that negative x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. Okay, great. Now we have constructed the desired inequality that contains the term that we're interested in the middle. Now we can just take the limit of each portion. So the limit as x goes to 0 of x squared less than or equal to the limit as x goes to 0 of x squared sine of 1 over x less than or equal to the limit as x goes to 0 of x squared. And the terms that we have on the left and right-hand portions of our compound inequality are polynomials, which means they're continuous everywhere, which means we can evaluate the limit via direct substitution. So we can just plug in. So we just plug in, we'll get -0, so 0. We have this term. Can't do anything with it. We'll just copy paste, literally. And this is 0. And if you've been watching the previous 2 videos, this argument then becomes, well, if this limit is between 0 and 0, there's only one real number that is simultaneously less than or equal to and greater than or equal to itself, and that has to be itself. So in this case, the squeeze theorem implies that this limit must equal 0. Okay, so as you can see in example 3, the only difference is this x squared just becomes an x. So I'm just going to copy paste all of this right down here, and then quite literally this argument works as if we never had those squares. Done. Just deleted all the squares. Everything else in that argument is the same.